Assalamualaikum and selamat sejahtera. Okay, today we are going to start with chapter 3, electromagnetism. Okay, in this chapter we have 5 subtopics. Okay, we begin with the first one, that is the magnetic effect of a current carrying conductor. Okay, here are example of simple device which use the concept. The first one is electric bell. The second one is the device to separate scrap iron and steel from trash. This is what we call a maglev train. By the end of the lesson, you will be able to state what an electromagnet is. Second, draw the magnetic field pattern due to a current in a straight wire, coil and solenoid. Okay, so let's look at the first one. What is an electromagnet?
You might already know about regular magnets. They have opposite poles that attract, similar poles that repel, and they can even attract other metal objects that don't attract each other, like these paper clips. You can also take a compass, which is itself a small magnet, and move it around near another magnet, and the needle will point in the direction of the magnetic field. So how does a coil of wire manage to behave the same way? It turns out that moving electrical charge, or current, creates a magnetic field. Watch what happens when I connect this piece of wire to a battery. It makes the compass needle move just like a magnet did, so we know the wire must be creating a magnetic field. This magnetic field takes a circular shape around the wire like this. However, the magnetic field around a single straight wire is very weak, not enough to pick up even one of these paper clips. You can make the magnetic field much stronger by wrapping the wire into a coil called a solenoid. This causes the fields around each individual turn of wire to add up to make a much stronger, more uniform magnetic field similar to that of a bar magnet like this. However, you'll see that this coil of wire is still too weak to pick up an individual paperclip. To make an electromagnet really strong, you need to add a ferromagnetic core like this iron bolt. Ferromagnetic materials have many smaller individual magnetic domains. Normally, these domains are aligned randomly and cancel each other out. However, in the presence of an external magnetic field, these domains align with each other and the external field, making the overall field much stronger. Watch what happens when I insert this iron bolt into the core of my electromagnet. Now it's finally strong enough to pick up a paperclip. Unlike a regular magnet, an electromagnet can be turned on and off by removing the flow of electrical current. If you reverse the direction of the electric current, you reverse the direction of the magnetic field. You might already know.
So do you get any idea what is an electromagnet? Okay, this is a picture of permanent magnet. Okay, so diagram shows a permanent magnet attract the nails, and here is the picture of an electromagnet. Okay, so the nail and the wire produce an electromagnet. Okay, now what is magnetic field? So magnetic field is a region where an object experiences magnetic force. When we put the steel here, it will attract to the magnet. Okay. Now, again, what is an electromagnet? So, electromagnet is a magnet made by winding a coil of insulated wire round a soft iron core so that a magnetic field is produced when a current is passed through the coil. In other words, electromagnet is a temporary magnet which is produced when current flows through a coil of wire wound around a soft iron core. So this is the wire wound around the iron nail or soft iron core. Okay, and here is the battery as the source of the current. In this case, we use direct current, and as we can see here, when the current flow, it will attract the paper clip. Okay. Now, how a magnetic field pattern is represented? So we draw what we call a line of force of the fields. We cannot see the pattern but we can draw the pattern by using what we call the line of force. So line of force shows magnitude of the magnetic field. If the lines are closer to each other, means that the magnitude of the field is stronger, and otherwise, if the lines are further, they will means that it is a weak magnetic field. Now, the direction of compass needle. So we put a compass on the line of force. So direction of compass needle will show you the direction of magnetic field. Okay, right. Now the right hand, we have what we call the right hand grip rule. Okay, so you have our right hand. So we grips the four fingers, and here is the thumb. Okay, the thumb shows you the direction of current. So here is up, means the direction of current, and the magnetic field, the other four fingers shows the direction of magnetic field. In this case, the magnetic field is what we call clockwise, anti-clockwise direction, right? Anti-clockwise direction. Okay. Wire carrying, so what determines the pattern and direction of the magnetic field? So we have a very simple activities in order to draw the magnetic field pattern and determine the direction of the magnetic field around a current carrying wire. So we have three activities. So the first one is what we call a straight wire, only one wire, and connect to the battery. Here is the cardboard. Another one, a cardboard, and then we have a coil, one coil to the battery, and here with another, we have many coils, what we call it solenoids. Okay, so what we do is we switch on the current battery so that current can flow, and we sprinkle iron fillings onto the cardboards, and we can see at the patterns of the magnetic field. Okay, so we start with the first one, a straight wire. So this is the experiment. So what we should look for the straight wire. Okay, so here is the patterns for the straight wires. Is the real experiment. Iron fillings. Here is the iron fillings, and here is the plotting compasses. It will display the pattern and direction of the magnetic field. So here is the pattern, and the compass shows you the direction of the magnetic field in the straight wire. So this is a straight wire. Now we can see here the pattern magnetic field form a concentric circle. So we have circles, right? So many circles here. Okay. The space between the circle increases as you move away from the wire. Means that the further from the wire, the circle increase. Okay, means that the magnetic field is weaker. Right. Now, how to draw the patterns? Okay, so here is the picture. Okay, we draw it. Okay, the current. First thing, you have to know the direction of the current. So the current will flow from here to positive terminals, goes to the downward. Okay, here we call it into the paper. So into the paper or cardboard here, and we draw it circle. We draw circle. Okay, so this is the circle number 1, circle number 2, and circle number 3. At least we draw 3 circles. Now the second part is the direction. So in order to know the direction, we use our right hand grip rule. So this time you put your thumbs downward because the current is into the paper. So the thumb direct downward, and we look at the 4 other fingers will give you the clockwise direction like this. Okay, so this is the direction of the magnetic field for the straight wire. Now, if you put a compass, it will show you the direction for in a clockwise direction. Okay, so like this. So this one move to the right. Okay, downward to the left and upward. So it looks like it will going clockwise direction. Alright. So now, if you change the terminals, so now the current flow from downward, upward. So this is what we call out of the paper. So the thumbs direct outward. So the other forefinger will look at in a counterclockwise direction like this, right? So it will move to the right, here it will move upward, here will move to the left. So it will look like it will circle in a anti-clockwise direction. Okay, here is how we get this now. So this is out of the paper, okay, out of the paper. So the thumb is outward and the other four fingers move anti-clockwise, okay. And here is the downward direction into the paper. So cross means into the paper. So the thumb point downward and the other four fingers will move in a clockwise direction. Okay. Alright, again, so we have here. So this is the concentric circles, right? Okay. Okay, settled. Now we move on to the next one, coil. Okay, this is the coil. So we have one coil, and here is the positive. So this is outward, out of the paper. Here is into the paper. So this we group separately. This is the straight wire. So it will produce a circular, okay, circular concentric circle. Same with this part. Okay. Alright, so how we draw the pattern? Okay, so here what we should look at the pattern. Okay, so let's look at how we draw the pattern. Okay, first we draw. Okay, I draw it again, the setup experiment. Okay, the coil. Okay, we connect to the power supply battery, right? So current flow from left out of the paper into the paper. Okay, now we draw from the top view of the paper. Okay. Okay, so on the left side is out of the paper, so dot, and right side is into the paper, right? So into the paper. Now the current out of the paper, dot. Okay, now we draw a circle for individual. Okay, one side, one circle. Okay, another one for the right side straight wire. Okay, right. Now we determine the direction, so use our right hand rule. Okay, so this will be anti-clockwise. Okay, and on the right side into the paper, so it will go clockwise. Okay. Okay, in the middle, both are moving outwards, so the magnetic field combine to be stronger magnetic field in the middle. Okay. So magnetic field line are closer, so both have the same direction. Okay. Alright, so that is the pattern for magnetic field for a coil. Okay, right. Next we move on. Okay, here is another one. Okay, here is where this is the one that we draw just now. Here is when we change the direction of the current. Okay, so the pattern is same, but the direction is different now because here move downward, here is outward. Okay, look at this, in the middle, the line are closer to each other, means they are stronger here because the direction of the magnetic field are same. So they combine to get a stronger magnetic field. Now we move on to the last one, solenoid. Solenoid means a coil, many coil together. Okay, so we form what we call solenoid. So this is a cardboard. Okay. Alright, so this will be the pattern. So it looks like familiar with the pattern of a magnetic field for a bar magnet, right? Okay, so here is the real magnetic field pattern. Okay, Okay, here is the bar magnet. So here is the pattern of the magnetic field for bar magnet. Now for solenoid, okay, how we draw it? Okay, first we have to know the direction of the current. So here is the positive. So you move here, move through the hole. So you move here. Okay, move here back downward. Okay, back again. Alright, so from here we look at the current will be upward, right? Okay, so how we draw it? First we have something like this. Alright, another one. Okay, and in the middle we draw a straight line like that. Okay, now that is the pattern. Now we determine the direction. In this case we need to know which side is the north pole, another one is the south pole, because it's familiar with the bar magnet, right? Okay, so in order to do that, we use our right hand grip rule, but in this time we change a little bit. This time the four fingers will show you the direction of the current, and the thumbs will show you the direction of north pole. Okay, so how we do this? Okay, first we determine the direction of current. Okay, right? Okay, turns around. Okay, upward, 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 outward. So we look here. So the arrow is outward, right? So what we do is we take our four fingers, okay, and make sure that our nail is outward like this. So means it follow the arrows, right? So it looks like the thumbs move to the shows you to the right. To the left, means that this is the north pole, and on the right is the south pole. So okay, so this is north pole and here is the south pole. Okay, that's how we determine the north and south pole for solenoid. Again, we look at here. Okay, so we have here. Okay, first determine the direction of current. So here look like this, means that our nail is going to be downward. So something like this, right? So nail downward, and look the thumb here to the right. So this is north, right? And on the left is south. Now we draw the needle direction of the needle of the compass. So north, so it will point to north. Okay, point to the north, and here we move to the left because it will move like this. Okay, from north to south. Now this one outward. So our our nails outward like this, and the thumb shows to the left, right? So this will be north direction, and this is south. Okay, so we complete the direction like this. Okay. Now let's answer some questions. What is the purpose of iron fillings? To show the pattern of the magnetic field. Okay, second question. What information can be obtained from the plotting compasses? Yeah, direction of magnetic field. What happens to the magnetic field when the supply connection are reversed? Yes, direction of magnetic field is reversed. And last question, what difference would you observe if the current in solenoid is increased? The magnetic field lines close together shows you that the magnetic field is stronger. Okay, so that's it what we learned today. So we continue next lesson. Okay, Assalamualaikum.